So yeah, thanks for coming to my talk. This is about rules IMG. It's a new way to build container images in Bazel. And it's a ground-up redesign that is really focused on performance. So I will start this talk by quickly explaining what container images are and how they work, just so you have the necessary background. And then we will compare the different ways to build container images in Bazel. And then we will go through the whole life cycle of building a container image. And I will explain you step by step what we do different to make this much faster. So first of all, a container image is just a nice way to distribute software. So you take the files that make up your final executable and any data dependencies. You package these up into layers, and then you add some configuration, and you can push that to a registry. And later, you can take this image and run it in Docker or in Kubernetes or in any other runtime. Foundational to containers is this OCI specification. OCI is the Open Container Initiative. And actually, there are three parts of this specification. There's the image format that defines how do you build an image and what does this format actually look like and what are the file types. Then there's the distribution spec that defines how do you talk to a registry to push and pull an image. And then the last part is how do you actually run the image. The last part doesn't matter for us right now. So next, let's look at a container image from the bottom up. So first, we are going to talk about layers. I always say a container image is just like a few tar files in a trench coat. And container image layers, they are just tar files. So here we have the lowest layer of your container. It just contains two files. And you could imagine now you add another layer on top. It contains another file, and you can continue doing this. You can also replace existing files and so on. And in the end, you take all of these layers, and you create a view that just combines all of them and overlays them. So that's just all that container image layers really are. And remember, these are just tar files. So next, we take the container image layers, and we hash them. We take the uncompressed tar files for this, and this creates something called diff IDs. And we take these, and we also take other configuration, like what should be the user that runs in the container, what are the environment variables, where do we want to run the command, what is the entry point, and so on. And we take all of that and just write it to a JSON file, and that's the image config. That's still pretty straightforward. And then on top of that, we have another abstraction. We have the image manifest. It just contains the hash and the size of the config that we just saw, and then also the hash and the size of all of the layers, but this time just the compressed layers. And then we have another abstraction on top of that. We just take individual image manifests. We take the hash and the size, and we give them a platform. So you can say, I have one image for AMD 64 and another one for ARM. And then you can just have a single image index to describe them all. So that's all that container images really are. Some tar files and then some JSON. And then there's another format that's relevant here. It's the OCI layout. It just takes this image. It always uses an image index as the entry point. And this image index references other files. And these are just stored in a content addressable storage. So there's a directory called blobs. And inside of that, there's a directory called SHA-256. And inside of that, all of the blobs are just named by their hash. And that's all that is. Yeah, and this storage format is important. And you will see it later on in the talk. So next, let's look at how you would usually build a container image. And usually, you would use a Docker file for that. And you can see it has multiple directives on separate lines. The first one, it describes what base image you want to use for your container image. The second one would set something in the image config JSON that we just saw. In this case, it sets the working directory. The third line just copies a file into a tar file as a layer. But then we see the fourth one. This is kind of special. We can actually take the existing layers and run a command on top of them. Just like we were to start a new container, take the existing layers, and run in that context. And that is pretty unique. And that is not how we build container images in Bazel. So in Bazel, we do something very different. You first build your application without any context to any base images or any other Docker ideas. You just build your binary. The binary has run files. You take the binary with the run files, you package it up as a tar, and then you can take this tar file and use it as a layer in your container image. And one very important differentiation is that we really don't need to know a lot about the base image to construct this. You basically build the application completely in isolation from the final image. So now with that context in mind, we will look at how this has evolved in Bazel. First, we started with rules Docker. It's the oldest one. It was initially just focusing on Docker. It was specific to Docker. Now it also supports OCI. It has a lot of nice optimizations that have grown over time. It still does not have official BZL mod support, and the reason is that there are a lot of language-specific ways to build container images. And this is very, very hard to maintain for the rules Docker maintainers. It also means that rules Docker has to be versioned together with all of these language rule sets, and that's very hard to do correctly. As a way to work around this, we later got rules OCI. It replaces most of the parts that rules Docker offers, but not everything. It strictly follows the OCI spec that I introduced earlier. They decided to have a very strict complexity budget, only use off-the-shelf tools. They do not use any Bazel providers, and everything is a file. So a layer in rules OCI is really just a tar file, and an image is really just a tree artifact. So it's a directory containing the OCI layout that I showed you earlier. So it's just a directory with all of the blobs inside. There are also no language-specific rules, and this makes it really easy to maintain. And it's an interesting trade-off. It's less performant. It gives you less language support out of the box, but it's very easy to maintain. And then rules IMG is somewhere in the middle. We follow the OCI spec. We try to optimize every step of the process of building a container image and deploying it to a registry. We do have custom tools written in Go. We do use providers to represent an image in the most efficient way possible. A layer is not just a single file, but it's actually a tar file and also a separate file containing metadata about the layer that we can use separately. If we pull a base image, we don't need to materialize all of the layers of the base image. We can avoid downloading them completely. And similar to rules OCI, we don't have language-specific rules. So in the end, the maintenance effort is somewhere in the middle, I would say. So now you may think of this XKCD. We had two ways to build container images. Now we have a third one. That's kind of annoying. You can keep this in mind. We will come back to it at the end. So now I will walk you through the whole life cycle of a container, from downloading a base image to building the layers, to assembling the config and manifest, and then to pushing it to a registry, loading it into a Docker daemon, or consuming the files. So first off, when you want to pull a container image, before rules IMG, so in rules OCI and in rules Docker, you had a repository rule that effectively downloads all of the blobs of the image from a registry. So that includes the manifest, the config, and all of the layers. And you have to keep in mind these layers can be huge. They can just be big tar files containing a lot of files. So this can be time-consuming, and because this happens in a repository rule, it all happens in one big step. And every Bazel user has to do that on their own machine. So instead, what we do in rules IMG, we only download the manifest and the config, and then we know about all of the digests of all the layers, but we don't actually download them. We just remember what registry we could fetch them from later. And what we notice is when building container images in Bazel, we don't actually need to access the base image layers at build time. We just create tar files and need to have the digests of the base image layers. So we can just avoid downloading them completely, and just later, when we upload the image to a registry, we can just make sure that the layers from the base image exist. And if they don't exist yet, we can stream them from the original registry at deploy time. So that's the optimization here. And then there's also another way. If you really, really need the layers of the base image, for example, you're doing an integration test where you actually load the image into a Docker daemon at test time, then we can also say you download the manifest and config in a repository rule, but you download the layers in a build rule. And the build rule will just access the internet in the execution phase. And this is much nicer because this can happen in a remote execution action, and it can also be cached in the remote cache. Yeah, so these are the options we give you for pulling an image, and this already makes it much faster when you work with large images. So next we will look at the build phase and how we assemble the layers. So in rules OCI, there's actually no way to build a layer. Rules OCI doesn't tell you how to do it. You can just use other rule sets that assemble tar files, and then you can pass the tar files to rules OCI. And I mean, that's a choice to make it simpler and easy to maintain, but it also leaves a lot on the table in terms of performance. In rules IMG, we do have a custom rule that can produce a tar layer, and it gives you a lot of optimizations. So the first thing, we see all the files that go into a layer, so we can deduplicate them. So if we see the same file twice, we just store it once, and we create a hard link for the second time. That means the image is smaller. The second thing we can do is we can use something called eStargz, which is a custom compression format that uses compression and a custom index into the compression so you can seek around in the image. And that allows you to deploy the image to a registry and then pull it later at runtime, and you can pull it lazily. So you don't need to pull the full image to run it. You can just pull the parts that you need at runtime. And that is something that is very hard to support otherwise. But the most important difference between these is that we write the layer into one file, and at the same time, we write the compressed and uncompressed hash of the layer into a second file. And that means we can later just use this metadata file instead of loading the full layer into any action down the line. One important thing to say is you can still use tar files as layers if you really want to, and that's very important when you migrate. But it's more efficient if you use the custom the custom rule that we offer. So next, we look at how to assemble a full image after creating the layers. In Rules OCI, we have a very big I/O bottleneck when it comes to creating the actual image. And this differentiation doesn't make a lot of difference as long as you run every action locally, because the files already exist locally and we can just symlink or hardlink them into the right place. But for remote execution, this is very crucial. So the way that this works in Rules OCI, the image itself is a big tree artifact containing all of the blobs. So if you pass a base image into the action, then all of the layers of the base image get passed into the action that builds a new image. And at the same time, all of the new layers that you want to add to the image also get passed to the same action. So when you want to schedule this action in remote execution, all of the layer blobs have to be loaded into the remote execution worker. And at the same time, the output of the action contains the sum of all layers of the input. So that just becomes bigger and bigger if you build layers, images on top of images. And that is very inefficient for remote execution. So in Rules OCI, in Rules IMG, we have the separate file containing only the checksums of the layers. So we only pass this in as action inputs. And as outputs, we only get the image config and image manifest. And these are tiny in comparison. So you will see a lot less I/O for this specific part. And it's really dramatic. On the left side, you could have gigabytes and gigabytes of file transfers if you're unlucky. So now that we built the image, we want to actually push it to a registry. And the way you do that in Rules OCI is you have a specific target that you Bazel run. And what Bazel does in the background is it creates a shell script as the entry point that will be run. And also in the run files of this shell script, you have all of the blobs of the image. And this way, when the shell script runs, it can talk to the registry, figure out which of the layers need to be pushed, and just push the missing layers. But if you use remote execution, then this is very bad because you could assemble the full image remotely. It lives in the remote cache. And just by creating this target that you can Bazel run, Bazel is forced to download all of the blobs to your local machine. So you destroy all of the benefits of Build Without the Bytes. And the way that we work around this, so first of all, in Rules IMG, we do have the same support. So if you don't use remote execution or you need something that always works, you can still do this. You can say, give me the push target and give me all of the run files. This still works. So what will happen is Bazel downloads all of the layers, adds them to the run files, and you can upload them. The next strategy that we have as an optimization is to just not add the layers to the run files. So in this setup, you have the push target. It is an executable file, and it contains only the manifest and the config and some extra metadata, but not the actual big layer blobs. So what we do now is the push target, this binary, it talks to the container registry, it figures out which of the layers still need to be uploaded, and then it talks directly to your Bazel remote cache, and it will just stream the missing layers directly from the remote cache and then to the container registry. And for incremental builds, this is a huge improvement. It means that for the most part, you can just stream a small layer at the end to the registry, but all of the existing layers don't need to be downloaded. but we do have some more strategies. The next strategy that we offer is a completely custom container registry. In this case, you have a similar setup. Your push target doesn't contain any layers in the run files. You only have some metadata about the image. And the container registry is now something that we offer as a custom tool in rules.img. And it is directly connected to your remote cache. So it's the same cache that you used during the build. And what we can do now is, at runtime, when you do Bazel run and then the push target, we just tell the container registry, here are the blobs of the image that I want you to serve. And nothing else happens, so we never actually upload anything. And then when someone wants to pull an image, the container registry can just talk directly to the Bazel remote cache and serve the actual layers. So this is obviously much more efficient. You only store the image once in the remote cache. The big downside of this approach is obviously that the Bazel remote cache does not give you any guarantees about the lifetime of anything you store. And for that reason, you either need to ensure that you copy any layers to some durable storage, or you should only use this for development. But it's still a very nice option. And then the third one, that's the one I would say you should use if you have a big organization and you want to centralize how you push your images, and you want to make it really fast. This is the build event stream method. So in rules.img, we also ship a custom build event stream listener. And the build event stream is just basically some extra telemetry that Bazel creates during the build. And you can just point Bazel at this custom build event stream listener, and Bazel will tell this custom backend, hey, I just built this image, and this is where it should be pushed. It's just part of the target definition in the build file. And then the build event stream listener can talk to your Bazel remote cache, learn about the image, ensure that all of the missing layers are pushed to a registry, and do all of that in the background. So here, you don't need to Bazel run anything anymore, and it all just happens in the background. And this scales very nicely because we can avoid a lot of communication to the registry by just caching and deduplicating requests. I should also say that this approach is not completely new. There was a talk at BazelCon last year by Sushain from Stripe. He did similar work for Rules Docker, but it was never published as code in the open. So this is the first time you can use this directly. So that's all the ways you can push an image. I think it's enough of ways that we offer. So now we will continue talking about loading an image into a container daemon like Docker. So that's another common setup. You may not just want to load it to a registry, but also just use it locally for testing. So the way that you normally do that is you use something called Docker save that takes an image from one Docker daemon and it writes it to a custom tar format. So it's just a tar file with a specific structure. And this file is then completely portable. You can copy it to another machine and then load it back in. And as you see here, this just uses standard input and standard output in Unix. And what you will also see is this is very inefficient. This tar file contains all of the layers of the image, and it doesn't care about what the other side might already know about the image. And still, this is how we normally load things into Docker. And it means that when we want to load an image from Bazel into Docker, we need to create this tar file just to then load the whole thing from start to end and then see we cannot actually make use of incremental builds because we still need to have the full thing. There are some tricks that rules Docker had that were not implemented in rules OCI and that we also don't implement in rules IMG, where you try to guess what layers are already in the Docker daemon, and then you give it fake blobs to make this tar file smaller. But it's a pretty bad hack, and we don't do that. So instead, we use the containerd content store. So in new versions of Docker, Docker is actually backed by containerd, and containerd exposes a nice content addressable storage behind the scenes, and you can access this via a socket. And this works very similar to the Bazel remote cache. You can ask, does this blob with this digest exist? Or you can say, load this specific blob into the content store. And whenever Docker uses containerd behind the scenes, you can just load the missing blobs into this containerd content store and completely avoid using the bad API of Docker load. So this allows us to do incremental image loading that is truly incremental. And right now this works on Linux. It doesn't really work on macOS because containerd on macOS runs inside of a Linux virtual machine. There are some hacks to get access to the socket, but I wouldn't recommend it. But Docker will soon offer the same content store directly on the Docker socket. So this will become the best way to load images on every platform. So we use this nicer backend if possible, and we will just fall back to Docker load if nothing else works. Now there's one last way you can write, you can consume a container image. You can just use the files of the image directly. And for rules OCI, the output of a container image rule is always a tree artifact with all of the blobs. So it's pretty straightforward to consume the image just from this output. For rules IMG, we don't do that by default because we want to be more efficient. And creating a huge tree artifact actually is bad for remote execution. So instead, you just get the manifest and the config by default. But we just give you a special output group that does give you all of the blobs. So if you want to have an image that is compatible to rules OCI, or that is just available to use locally as just a set of files, you can just build the output group and you're done. So that's another way you can consume the image. So that leaves us with the following question. Should I migrate? And the answer is, if you use remote execution, then yes. It's pretty clear because otherwise you can just revert to doing your image building locally and doing the rest remotely. Everything else just doesn't make sense in terms of performance. But if you already migrated to rules OCI and it's just very expensive, then I mean, it's just fair to say there's no big difference if you use local execution only. So it still doesn't hurt. So this leaves me with the conclusion to the XKCD. We now have 2 competing standards, or 3. I think in the end we should just join forces and try to solve the actual problem and have a fast solution for everyone. All right, yeah, that was my talk.
Hi there. might suggest that you could have even more ways of pushing than the many ways that you described. I'm curious, in the way that you described that has the custom container registry that's situated near the cache, is there a configuration to where you can have it proactively just go ahead and pull from the cache so you don't have to worry about cache lifetime?
So you want to proactively pull from the cache to the registry?
Yeah, so it'll be persisted.
Right now, it does not have any persistent storage, but...
Oh, I see. So in other words, if you have like 10 pods that come up, it's going to go and get it from the cache 10 times?
Yeah.
I see. Okay.
Yeah, but it's not that hard. You could add it. Yeah.
I see. Maybe along the same veins, I'm wondering, did you think about having something kind of in between, yet another way of pushing, where you can continue to use your ordinary container registry that you're used to using, but you could have like a proxy container registry that you push to that would go and be situated near the Bazel cache and do that little dance.
Yeah, definitely. I also think what you could do is just inform this registry about the blobs and then just promote the artifacts from the remote cache to some permanent location. Yeah, definitely.
Yeah, this is very interesting. Thank you.
Hey, congratulations. This is a really good thing to see finally realized after many years of struggle with Rules OCI personally. I just want to give 2 points. One is feedback and one is a question. The feedback is, I think the decision tree not based on remote execution, but as long as you use any sort of remote cache, you do want to switch because the blob that currently being output by Rules OCI are pretty big and they can invalidate and increase the total size of your remote cache by quite a bit and then therefore usually reduce the TTL of the cache. Right, so the moment when you switch to rules image, I would expect your remote cache to run a lot more efficiently. Right, so that's for the decision tree. I also want to ask if you can comment on how rules image could handle all of the authentication with the remote service as well as the registry that you're pulling from and you're pushing to. If you can comment on the authentication.
So the authentication from the push binary to your remote cache uses the Bazel credential helper protocol. So you can just use the Tweag credential helper to get, for example, a token from Build Buddy. That already works. And then for container image registries, we use Go container registry, which just reads your Docker config. So if you have a token in there and you use Docker login, then you can also push to a registry successfully.
Yeah, I just want to echo what Sun said. It's such tremendous work. It's like when you explain it, these ideas are so obvious, but yet somehow it's taken 10 years to like discover this. So really great job. My question is about your choice to use like network access during actions. And I've always thought that was kind of like an anti-pattern and sort of like a dirty thing to be doing. Yeah. Should I revise my thinking on that, or how did you think about that?
I would say for Bazel 9, we get the remote repo contents cache. And with that, you might no longer need this specific trick. We have actually 3 ways. You can either completely avoid the layers and just not have them for tests, or you can eagerly download them, just like Rules OCI, which is slow, or you say, I accept that my build action accesses the internet and therefore everything uses remote execution. So it's a trade-off and you can decide.
Okay, thanks for the great talk and the great work here. And I think definitely more people are interested in this, so please continue the discussion, but we have to move on due to time limit. So next we have Rajiv and Naman talking about Go, WebAssembly Bazel, and building for hermetic high-performance web application.